In this video, we shall look at a few review problems associated with conservation of linear momentum. The conservation of linear momentum says the initial linear momentum of the system is the same as the final linear momentum of the system. This is true provided there is no external force or forces is acting on the system. Example of external force or forces are friction, air drag, and so on. Now let's look at the problems. A bullet of mass 12 grams strikes a ballistic pendulum of mass 3 kg. So this is the mass 3 kg and this is the bullet. So this bullet travels initially with speed u meter per second, strikes this mass, and the mass as a result rises a vertical distance of 15 cm while the bullet remains embedded in the mass. Calculate the initial speed of the bullet, that is u. Let's apply conservation of linear momentum. First, the moment just before the bullet hit the mass while it was traveling with that speed u meter per second is the initial state. And just after it strikes, the whole system, meaning bullet and the mass, will start to move with some other speed v. And that is the final state. So let's relate these two states through conservation of linear momentum. Initial momentum, that is the momentum of the bullet, is the mass of the bullet, which is 12 gram converted into kg, times its speed, which we are interested in, must be the same as the momentum of the system after the impact. Remember, before the impact, the mass is not moving, so it does not contribute anything to the initial momentum. As soon as the impact occurs, the bullet and the mass become one system. So the total mass is 12 gram plus 3 kg. So that's going to be 3.012 kg. And the speed after the impact is v, so which we also don't know. But we can figure that out. So let's call this equation equation 1. The next step is to apply the conservation of energy, or more precisely mechanical energy. The initial state for this analysis will be the state with the bullet inside the mass after the impact, and the final state is when it rises to that maximum vertical height of 15 centimeters. You see that at this position, the energy is purely kinetic. Now we shall take the potential energy at that level to be 0 joule. So the kinetic energy at the initial state is half times the total mass, which is 3.012. This is the mass of that pendulum plus the bullet, v squared, the v which we don't know. We have taken the potential energy there to be 0 and equate that to the energy at the final state. At the final state, it comes to a complete rest. So in this state, the speed is 0 meter per second, so there is no kinetic energy. However, there is gravitational potential energy involved due to this 15 cm rise, and that's given by the mass 3.012, gravity 9.81, times the rise in meters, so 0.15. From this equation, we can solve the v, which we need to solve u from equation 1. And when you solve for v, you get 1.72 meter per second. Substituting the value that we have found for v inside equation 1, you can determine that little u. So your little u is 3.012 times v, which is 1.72, over 0.012, which will give you 432 meter per second. And that is the initial speed of the bullet prior to impact. Problem 2. An object initially at rest at the origin of an XY coordinate system disintegrates into 3 pieces. So that is the initial object. It disintegrates into object 1, object 2, and object 3. Immediately after disintegrating, one piece of mass m moves with velocity 20 meters per second along the negative x-axis, so that is object 1. The second piece with same mass m moves with velocity 20 meters per second along positive y-axis, so that is object 2. The third piece has mass 4m, so that is this one. Find the velocity, the magnitude, and direction of that third piece. So this is the initial state, and all this is the final state. So since the object was initially at rest, the initial momentum of the system is 0. Now let's look at the final momentum of the system. So the final momentum of the system has 3 pieces. The first one is the momentum of object 1. We know the mass is m, and the velocity is 20 meters per second to the left, so it's minus I hat, like that. To that, you have to add the momentum of the second piece, the mass of which is also m. The velocity is 20 meters per second in a positive y-axis direction, so that means it's j hat. That's represented by that arrow. Now the momentum of the third piece, which is the mass is 4m, velocity we don't know, that's what we want to find, so let's denote it by v. Conservation of linear momentum says the initial linear momentum of the system must be the same as the final linear momentum of the system. In other words, you must equate this entire thing to 0. So the m goes away, and you can solve for v, and that's going to give you the vector v as 5I hat. It's 5 because it's 20 divided by 4, minus 5j hat. So that is this 20j hat. Bring over to that side and then divide that by 4. Note the unit is meter per second. Now we can determine the magnitude of this velocity, or the speed that is. That is 5 squared, so it's 25, plus minus 5 squared, so that's another 25 square root, which will give you 7.07 meter per second. What about the direction for this vector v? From the vector expression, we know that the x component is going to the right, 5 meter per second. The y component is going down, with also 5 meter per second. So that means the angle is given by that angle alpha. So from trigonometry, alpha is arctangent, the vertical component, which is 5, and the horizontal component, which is 5, and you get 45 degrees. So we define the direction of this vector v as 45 degrees below the positive x-axis, because this direction here is positive x-axis, so alpha is defined as 45 degrees below the positive x-axis. Problem 3. An 80 kg person pushes a 60 kg mass away from him on a frictionless surface, so there is no friction here, with a speed of 2 meters per second. What speed does the person acquire as a result of his actions? So this is the initial state, and this is the final state. And the force that is used to create the final state is internal force. So the internal forces acts in pairs. So conservation of linear momentum still hold. At this stage, none of the components of the system are moving, so the initial momentum of the system is 0. At the final state, we know that the box or the mass is moving to the right with a speed of 2 meters per second. So the final momentum of the system is the momentum of the mass, which is 60 kg times 2 times I hat, due to that direction, plus the momentum of the person who's moving in an opposite direction. The mass of the person is 80. We don't know the speed of the person, so let's just write it as v. From conservation of linear momentum, this must be the same as that. So 0 equals 120 I hat plus 80 times that vector v. And you can solve for vector v, which is minus 1.5 I hat meter per second. So the person acquired the speed of 1.5 meter per second and in the direction of minus I hat, the leftward direction that is. That solves the problem. Problem 4. A 25 kg body moves along a positive x-axis with speed 300 meter per second. It breaks apart due to internal forces into 3 parts. Part 1 with mass 15 kg moves away with a speed of 100 meter per second along positive y-axis. Part 2 with mass 5 kg moves away with speed 450 meter per second along the negative x-axis. So what is the velocity of the third part, and also calculate the energy that is released during the breakup. So the initial state is the state where this 25 kg body moving to the right with speed 300 meter per second. So that momentum, the initial momentum of the system, is just 25 times 300 I hat, which is 7,500 I hat kg meter per second. Now the final part. Part 1 with mass 15 kg moves with speed 100 meter per second along the positive y-axis, so that means that way. Part 2, mass is 5 kg and it moves away with 450 meter per second along the negative x-axis, so that means that way. And part 3 with mass 5 kg, now how do we know it's 5 kg? 15 plus 5 plus 5 must equate the original 25 kg. So this 5 kg, the third 5 kg, it's moving with some velocity v, which we are interested in. So let's write down the final momentum of the system. So for piece 1, it's 15 times 100 j hat due to that direction. For the second piece, it's mass 5 kg and the speed is 450 minus I hat because of that direction. And the third piece is 5 times vector v. And due to conservation of linear momentum, equating these two, we can figure out the vector v, which will give you 1,950 I hat minus 300 j hat meter per second. So that is the velocity of the third piece. Now let's calculate the energy that is released during the breakup. So according to conservation of energy, the initial energy of the system, which is the kinetic energy, have 25 times 300 squared, plus an internal energy of that system that is eventually released when it gets to the final state. So this is what we are looking for, equals the kinetic energy of the system in the final state. So the first piece is half, mass is 15, the speed is 100 squared. Then the second piece is half times 5 and the speed is 450. Don't forget to square. Plus the kinetic energy of the third piece, half times mass 5 kg times the square of the speed. Now we have to find the speed. That can be determined from the components of the velocity. The speed squared is just 1950 squared plus minus 300 squared. Putting this inside here and solving for EI, we can get the energy that is released during the breakup. And if we do that, we find the following for E sub I, which will give you 9,187,500 joules. And that solves the problem. Thank you for watching.